Okay, now let's consider this. What change in velocity is required to increase the kinetic energy of an 8 kilogram mass by 10 joules? And actually, I'm going to give this 40 joules, okay? So when it increases by 40 joules, if the initial velocity is 1 meter per second, okay? Well, we know the change in kinetic energy is equal to the change in 1/2 mv squared. Okay? And that equals 1/2 mvf squared minus 1/2 mvi squared. Well, let's work it out with the numbers. We could work it out with the symbols and get a result, but that's not going to lead us exactly where I want to go with this. Because I want to then ask the question, what's the change in velocity, if the initial, or what changes required if the initial velocity is 2 meters per second or 3 meters per second. Okay? So I'm going to go ahead and work it out with the numbers. I'm going to say that 40 joules equals 1/2 of 8 kilograms times Vf squared minus 1/2 of 8 kilograms times Vi squared. Of course, we know Vi. It's 1 meter per second, and it's going to be squared. We know that. So that, well, you do this, and you get 4 joules here. So, simple rearrangement. Half of 8 kilograms is 4 kilograms times Vf squared. That's this term. And it's going to equal what we get if we add this to both sides. And this being negative 4 joules, when we add it, we get 44 joules. So Vf squared, well, I'm not going to go through the details. We're going to divide 4 into 44. We're going to get 11. And it's joules over kilograms equals, and you should write out the steps, but I'm not going to. Comes out square root of 11 meters per second, which is approximately 3.4 or 3.5, 4, 12, I think it rounds to 3.5 meters per second. Okay? So that's pretty straightforward. So what's the change in velocity? Well, from 1 meter per second to 3.5 meters per second. We get 2.5 meters per second. Can't read that sloppy meter per second there, but I understand. Okay. Okay, well, so we think that a change of velocity of 2.5 meters per second should result in a change in kinetic energy of 40 joules, right? Let's just test that out. What if the initial velocity is, let's say, 3 meters per second? Fully expecting to get 2.5 meters per second because it's obvious we ought to have the same change in velocity. Well, actually, turns out we don't. So we could set it up again. We have 40 joules. One-half mvf squared minus, well, 1/2 of, I have room to write it. Okay, same equation we had before, but its initial velocity is 3 meters per second. And of course, when we square that, we get 9 meters per second. Multiply that by 8 kilograms, or half of 8 kilograms, we get 36 joules. So we're going to end up with 76 joules. Okay, well, that's different than the 44 joules we had before, but that's not surprising since we have a different number here. And we solve this, okay? You're going to divide this by 4, you're going to get 19, and you're going to get VF equals the square root of 19 meters per second. Put some dots in there, easily do those steps. And that's approximately 4.3 meters per second. So delta V is obviously going to be 2.5 meters per second, but let's just check it out. Okay, well, delta V is VF minus VI, which is 4.3 meters per second minus, what do we have, 3 meters per second. Obviously, that's 2.5, whoa, wait a minute, that's only 1.3 meter per second. Okay? What's this foolishness? It came out different. Okay? Well, there's something to be learned here about kinetic energy and velocity. And we probably want to analyze it mathematically, but really we want to work this into our concept of what's going on. Okay, so let's just look at the general solution for the equation delta KE equals 1/2 m VF squared minus 1/2 m VI squared. Okay? Well, in this case, VF is going to be, and of course this should be a plus or minus square root. Well, this will be plus or minus. And I'm not going to worry about the plus or minus here. I'm worried about the nonlinearity of this thing. There's more to say about that plus or minus. Okay. If we went from 3 meters per second to negative 4.3 meters per second, the kinetic energy would be the same. Change of kinetic energy would be the same, but we'd have a much bigger change of velocity, wouldn't we? So that's something that's also worth pondering. But let's go to the nonlinearity thing here we're trying to get at. Okay, if we solve this, we get VF equals the square root of, we're going to add this to both sides. So we're going to have our delta KE plus the 1/2 m VI squared, but then we're going to multiply by 2 over m. So we're going to get 2 times the kinetic energy over m minus VI squared. Okay? And there's a plus or minus on this. And how does, so the change in velocity is the square root of 2 times the kinetic energy over m minus VI squared minus VI. Okay? Well, this is not a simple relationship, and there's no way you can expect that when VI changes, the delta V is always going to be the same. Okay? So the least we can say is a different delta V And we can also, if we do just a little algebra analysis on this expression, see that the bigger VI is, the less your delta V is going to be. Okay? You can just think about it. If VI is really big, then the square root here is going to be pretty close to VI, isn't it? Okay? But it's going to be you know what? I looked at that, I was getting something that was totally wrong because I wrote this down wrong. I'm going to add this to both sides. It's not going to be minus on this side. Okay, so now what I was going to say is going to make sense. Okay, so if VI is really large, then this is, well, this always has to be bigger than this, right? Because this is always bigger, well, what's inside here is always bigger than VI squared, so the square root is always bigger than VI. Okay, so if the square root is always bigger than VI, then your question is, as VI gets bigger and bigger, what happens to the difference between these? And you could just reduce this to absurdity with a numerical argument, much less an algebraic one. We can make the algebraic argument, just manipulating this expression a little bit. But let's just say that VI is 1,000 and 2ke over m is 1. Then you have the square root of 1,001. Sorry. VI squared would be 1,000,000. So you have the square root of 1,000,001 minus 1,000. Okay? There's not much difference. There's not much difference of what's in here, which would be 1,000,001. And if it was 1,000,000. Of course, if it was 1,000,000, these things would be equal. Okay? If VI is much smaller, then what's under here is going to be much bigger than VI squared, and the square root will be much bigger than VI, and that'll give us a bigger difference in delta V. Not sure I explained that real well, but just think of what happens if VI is very large compared to this, and what happens if it's very small compared to the 2ke over m. You'll see that if VI is small compared to this, you're going to get a bigger delta V than if VI is large. Of course, you can always take your graphic calculator and plot this expression. If you know enough graphing, you don't need a graphic calculator to do that, and hopefully you will develop enough graphing, although you've been ruined on that by having a calculator in your hands while you were learning to graph. But still, you want to think about how you would graph this thing, how you would analyze this thing. Okay. So there's a deeper insight to be gained here. That's what I'm saying. There's a deeper insight into why this delta V is less than that. And it's simply because VI squared is a bigger proportion of 2ke over m if you have a greater initial velocity than if you have a smaller one. I don't want to go too much further with that because it's something I just want you to think about.